So this is now the 6th lecture of the course in collider physics. I must make a brief apology that last night the organizers took the lecturers out for a very nice dinner, which included an enormous beefsteak Fiorentina, probably large enough that there was no reasonable expectation that I would actually make it up the hill this morning to give this lecture. But I did gain an enormous amount of mass, and so that makes it appropriate this morning to talk about the theory of the Higgs boson. So that's the topic for today. So as always in this course, I assume that you folks have the theoretical foundation in the Standard Model. So you've discussed what the Higgs boson is, the fact that it spontaneously breaks the symmetry of SU2 cross U1. What we want to do today is to talk about the properties of the Higgs boson, as it were, that would be seen in experiment, and talk a little about the status of the experimental exploration of the properties of the Higgs boson. So with that, let's just get started. Now, the Higgs boson has, at the level of the Lagrangian, an exceptionally simple scheme of couplings. Because, as again, I hope you have all studied in the past, the Higgs field appears in the Standard Model Lagrangian as a two-component complex scalar field. But then what you can do is immediately go to unitarity gauge. And in unitarity gauge, you gauge away most of the components of this field, and the only thing that's left is the vacuum expectation value of this field and h of x, the Higgs boson field. So what that means is wherever V appears in the Lagrangian of the Standard Model, the Higgs coupling just goes along with it. And if you like, we can write 1 plus h over V. So what that means is that the Higgs boson in the Standard Model has a very simple structure. It only couples where a mass term is generated. The coupling is always perfectly diagonal. It doesn't change flavor. It doesn't change a vector boson species. This is not true in models that are more complicated than the Standard Model. For example, models that have two vacuum expectation values, or models that have composite Higgs and so on. But today what I'm going to do is really, we'll stick to the Standard Model, we'll calculate the properties. I think whether you believe or not that the Standard Model is the whole story of spontaneous symmetry breaking in the SU2 cross U1 theory of weak interactions, it is a very important reference point that you have to understand the properties of more complicated theories. Okay, well, once I've written this down, it's just immediate to write down the couplings of the Higgs boson. Why don't I just do that over here for reference? If I have a fermion, I look at the fermion mass term, the Higgs boson just couples in that way, mf over v. In the gauge boson mass term, W or Z, let me just write V here. The mass term involves the vacuum expectation value squared because it's quadratic in masses. And so I get 2I mv squared over the Higgs vacuum expectation value. And actually, even for the Higgs boson itself, the trilinear coupling has a very simple form, 3I m Higgs squared over V in the leading order. So there's nothing hard about the Higgs boson couplings. You always just take the Lagrangian, V, or differentiate with V, and that's the coupling of the Higgs field to whatever you have. But now what we're going to see is that the physics that comes from these very simple couplings has a lot of subtlety in it. And so the next thing that I want to do is to go through the various partial widths for the decays of the Higgs boson. And we'll see that really there's actually quite a bit to say about that. So the most important thing that you learn on this blackboard is that the Higgs boson couplings are proportional to mass, or in the case of vector bosons in general, to the mass squared of the particle. And so what that means is that the most important couplings of the Higgs boson are to the heaviest particles in the Standard Model, which are W, Z, and top. And so naturally what you would expect is that the most important decays of the Higgs boson would be, for example, to TT bar, W plus W minus, and ZZ. And for, let's just say, well, maybe I should say, when the Higgs boson was first introduced, that was the expectation. But now we've found the mass of this particle, and the mass of the particle turns out to be about 125 GeV. And that number is very relevant right here, because if the Higgs boson has this mass, all three of these decays are kinematically forbidden. And so what we have to do then is to look kind of down the hierarchy of particles in the Standard Model and try and find the next most massive ones. And those are the ones that are going to now dominate the Higgs decays. But then there's going to be another subtlety, that because these couplings are so large, these couplings are important also when W, Z, and top are off-shell. And so then we're going to get actually a long list of decay modes, all of which are realizable at the percent level or the tens of percent level. And actually, this is one of the very fun things about Higgs phenomenology, that there are a very large number of decay modes, all of which you can figure out how to access in one way or another. And so nature has given us this tremendous opportunity to test these simple values of the couplings in many, many different ways. And I think it's going to be a very important theme of particle physics, probably over the next 20 years, to actually go through and test all these couplings and really see, is this simple theory everything, or are there corrections to it? So very likely, if you go into collider physics, this is going to be one of the main things you're going to be thinking about in your career, and I have to at least get you off on the right track. Okay, so let's now start computing Higgs boson partial widths. So the easiest one is Higgs 2 fermions. And maybe you should say, if you remove these decay channels, the next most massive particles in the Standard Model are BB bar and tau plus tau minus. And so the next order of business is to compute the partial widths to these channels, which at least will make up a large part, if not all, of the total Higgs decay width. These calculations are really easy. Let's think about Higgs to please excuse me, B, let's say B right, B bar right. The coupling here is a chirality flip coupling. So this is the right orientation. The matrix element in terms of, for particles that are lighter than the top quark, it's a good approximation to ignore the mass of the quarks except where it appears in the coupling. So I'm going to do that in this calculation. Then I have minus I mb over v, u dagger r v r. This is a scalar. I can put those in any orientation. So, for example, 1, 0, and here minus 1, 0. So we get the simple answer mb. Oh, and no, I'm sorry, and there's a square root of 2p squared. Square root of 2p is just the Higgs mass. So we get this very simple answer. And so then you can work out the partial width. In general, for Higgs to FF bar, 1 over 2 mh, 1 over 8 pi, the square of this thing, mf, m Higgs squared over v squared. There's a factor of 2 because I can also have b left, b bar left. And so this then comes out to alpha weak over 8, mh, mf squared divided by mw squared. Okay. Actually, it's not so hard to go back and include the fermion mass. And I think it's useful just to write that formula. Alpha w over 8, mh, mf squared over mw squared, and then the factor comes in 1 over 4 mf squared over m Higgs squared to the 3/2. It turns out that a scalar decaying to 2 fermions, it's in the p wave. So you see that here. Okay. Now, at this point, we can plug in some numbers. And for the case of leptons, for example, tau and mu, you literally can just plug the numbers into this formula and get a very accurate answer. EV. For the mu, a much smaller number, 9 keV. For quarks, though, there are more things that we have to think about. And basically, there are 2 considerations which are very important in understanding quantitatively what the predictions of this formalism are. The first one is fairly straightforward. Just like in Z to QQ bar, there's an order alpha S radiative correction. So when we have the Higgs decay to BB bar, you can radiate gluons and more gluons. And so there's a QCD perturbation series that one should sum up. Actually, the group in Karlsruhe, Cheturkin and Kuhn, have done and Baikin, please excuse me, have done a huge work with this. So this perturbation series is actually known to n to the 4th LO. It's a heroic calculation. The leading term turns out to be rather large. It's 1 plus 17/3 alpha s over pi. Let's renormalize it at the mass of the Higgs boson. There are more terms. Eventually it adds up to about 1.24, which is quite a large correction. But there's one more important thing to worry about, and that is that when you evaluate this formula for quarks, you should actually evaluate it with the fermion mass evaluated at the mass of the Higgs boson. So when you renormalize this formula, what you would get here is the ms bar mass, for example, of the fermion evaluated at the mass of the Higgs boson, 125 GeV. And that actually makes a big difference, because as you folks I hope all know, a quark mass as a function of q decreases as a power of a logarithm of q. So the formula for this is mf of m Higgs is equal to mf of mf, which are the usually quoted ms bar masses of quarks. And then there's an alpha s of mh over alpha s of mf to the 4 over b0, where this is the beta function of QCD. And then there's a series of order alpha s corrections to this formula. Anyway, when you get everything straightened out, what you get are quark masses effective for the phase, which are very different from the ones that you've seen in your textbooks. And so let me just write for U, D, S, C, and B. Masses that go into the evaluation of this formula are something like 1.5 instead of 2, 3, 60 instead of 100, 700 instead of 1200, and 2800 instead of 4.2. And that actually makes a difference, as we'll see in a minute. So putting those numbers in, for example, gamma h to bb bar is, okay, we have all the ingredients here. Alpha w over 8, we know what the Higgs mass is. For the mass, I'm going to take this number, this term, and then the QCD correction. And when you put in all the numbers, you get 2.4 MeV. It turns out when we evaluate the other Higgs decays, which I'll do in the course of this lecture, this turns out to be the total width of the Higgs times a branching ratio of about 58%. And so the total width of the Higgs then, as we'll see, accumulates to about 4 MeV. So this is the next thing which is important to know about the Higgs, that its decays are dominated in the standard model by Higgs to bb bar, and that it's a very narrow object. 4 MeV, it's 3 orders of magnitude more narrow than the W or the Z. And this number is just incredibly difficult to measure at a collider. There's really no strategy at any collider that gets you there, I think, in any foreseeable circumstance. So if you try and measure this number, you measure it indirectly in some way. Okay, well, again, in these numbers for the other quark species, the branching ratios are B, tau, charm, strange, and mu. So here, 58%. These get smaller and smaller as the mass decreases. So for tau, the prediction is something like 6.3%. For charm, 3%. For strange, 0.03%. And for the muon, 0.02%. I think it's actually realistic to think that, this number can be measured at the LHC eventually. The Higgs to mu decay is a very striking signature. You have a muon pair. You can measure the pair mass accurately, and you know where it's supposed to be. It's supposed to be at 125 GeV, and gradually we'll measure that number more and more accurately, so you know exactly in what bin to look for an excess. Nevertheless, we've discussed a large number of mechanisms in this course for creating mu pairs, and so it's a tiny signal over an enormous background. But it's considered this number can actually be measured eventually in the long term in the LHC program. These two, I'll talk about the status today. Charm is a really interesting mode because you would like to, for example, compare the up quarks and the down quarks in relation to their coupling to the Higgs boson, and measuring the Higgs decay to charm is one way to do it. Unfortunately, charm is typically a quantity. You would find charms by displaced vertices, but the B is much longer lived. And so the B is always you always have to disentangle the charm signal from a B signal in a practical collider setting. And with the B 20 times larger, it's just an incredibly difficult thing to do at the LHC. Strange, it's even more difficult. So somehow these processes may be difficult to measure at the LHC. These, I'll tell you what the status is later in the talk. Okay, so that talks about the fermion decays of the Higgs. Now let's talk about the vector boson decays of the Higgs. So I've already explained to you that the on-shell vector boson decays of the Higgs are kinematically allowed. Yes, the are very large. And so that should mean that it's interesting to think about off-shell decays of the Higgs to WW and ZZ. So what you have here is a situation where you produce a virtual WW or ZZ. Those particles then decay to some fermion final states. And what you end up with is a Higgs decay to 4 final fermions. The case of Z is particularly interesting because you can imagine that you decay to pairs of leptons, and then you have a set of 4 leptons which are totally visible in the LHC detectors, which are supposed to sum up to the mass of the Higgs boson. Unfortunately, the rate of this process is very low even before you consider the branching ratio of the Higgs into this mode. Because you remember that the branching ratio of the Z boson to an electron pair or a muon pair is only 2.3%. And if I include both of them, I get this number. If I square it, I get, please excuse me, 0.2%, even before I consider the Higgs branching ratio into this channel. So it's just, it's just very challenging in terms of rate to study these decays. Nevertheless, they're quite interesting, as I'll point out in a moment. Okay, now, the form of the vertex that we have here, it's indicated by the coupling that I've written on that blackboard. So the vertex, for example, for Higgs to ZZ, the matrix element, if the Z's were on shell, would be 2I mz squared over V, the polarization vector of the first Z dotted into the polarization vector of the second V. And this is something that we saw in the lecture yesterday. This is the kind of quantity which, if the bosons are on shell, actually even if they're not on shell, this evaluates to P1, P2 plus E1, E2 divided by mz squared. And so this is something which is of order the Higgs mass squared divided by 2 times the Z mass squared. So there's actually an enhancement in the case where both Z's are longitudinally polarized. So this is the thing that I talked about in the previous lecture. And here it turns out to be a rather important effect. If you have a decay to longitudinally polarized Z's, you get this enhancement. That enhancement factor actually has the properties that we talked about yesterday in top decay. M Higgs, you remember, is the square root of 2 times lambda, the square root of 2 lambda V. So putting that factor together with that factor, you get mz squared over V times mh squared over 2mz squared. So this all adds up to mh squared over V, which is 2 lambda. And so what this factor does is, just as we saw for the top quark yesterday, it trades a gauge type coupling for a Higgs sector type coupling. So that, because the Higgs is actually heavier than the W and Z bosons, excuse me, this can be a dominant effect. Well, this is interesting for the following reason. Let's imagine that we, working extremely hard, managed to collect some events of this type at the LHC, where the Higgs decays to ZZ star, each Z decays leptonically, and then we get a 4-lepton final state. Now, we've measured these 4 individual 4 vectors, and there's an enormous amount of information that's contained in that system. So roughly, we have the decaying Higgs boson, we have the 2 virtual Z bosons. Each set of leptons gives a decay plane, And you can analyze all of the angles which appear in this decay process. There are two quantitative features that are very important. First of all, if the longitudinal z dominates, as would be the prediction of the standard model, that means that the cosine theta is central on both sides. So you can test the polarization even of the off-shell z by looking at the cosine theta angle in the decay. Secondly, the coupling epsilon 1 dot epsilon 2 implies that the decay planes are parallel, or tend to be parallel. And so there are two very striking features of this, which are very peculiar to the specific form of the coupling that comes in the standard model. A central distribution of cosine theta and the two decay planes being parallel. In contrast to this, if that particle at 125 GeV were a pseudoscalar, it presumably would have a coupling which would look like this. Delta L is my pseudoscalar particle now, and then I need something like epsilon mu nu lambda sigma, F mu nu, F lambda sigma, where F mu nu is the Z field strength. This has just the opposite set of predictions. The Z's, which are produced by this operator, are transversely polarized, which means that the cosine theta distribution is at the ends rather than in the middle. And because of the epsilon symbol, it's the cross product of the two polarizations. So the two planes of polarization are orthogonal instead of parallel. And so if you collect events of this kind, Higgs boson to 4 leptons, it actually doesn't take many events in order to discriminate these two hypotheses. And so I think both ATLAS and CMS have done this analysis, and it's really quite powerful. The total number of these events, as I'll show you in a moment, is of order 10 to 15 per experiment. But then if you feed them into these predictions and calculate the likelihood distribution, these two hypotheses are actually separated by about 3 sigma with this very small event sample. And actually, the CMS experiment, and I think also now the ATLAS experiment, have gone through and tested a number of hypotheses for the spin parity of the 125 GeV resonance using this kind of technique. You write down the effective operator that generates the two Z's, you decay the Z's according to the known pattern, you then figure out what the distribution should be of the event shape variables using all the angles that are apparent in this decay, and you compare the likelihood distributions. So if you look at figure 2 now, this shows some comparisons of these likelihood distributions from the CMS experiment. So in particular, the one in the upper left-hand corner is the comparison that I've just described. The 15 events found by CMS give you that little red arrow in that figure, and you see that it's highly consistent with the standard model coupling and quite inconsistent with a coupling of this pseudoscalar type. Now, you might ask, is this resonance at 125 GeV something that has some other spin parity assignment? So in just a moment, I'll talk about the Higgs decay to 2 photons. But let me just say that this decay has been observed. And actually, there's a theorem due to Landau and Yang that this forbids spin 1 for the resonance. The explanation for that, the first layer, is really pretty simple. If I have an S-wave decay into 2 photons, the two photons are always transverse. So there are only two types of helicity assignments. If the helicities are the same, you get j equals 0. If the helicities are opposite, you get j equals 2. This is for the S-wave decay. And you never get j equals 1. Now, it's a little trickier to generalize this to an arbitrary partial wave decay, but that's what these people did. You use Bose statistics. And basically, all the possibilities you can write down for spin 1 eventually lead to an antisymmetric wave function between the two photons. So you just can't do it. So given that this decay exists, we already know that that this 125 GeV resonance either has spin 0 or it has some higher spin. For spin 2, there are, I think, 3 different parameters in the couplings that you could put for the spin 2 particle to decay to 2 Z's. And so there are specific points in that space that have been explored, and that, I think, corresponds to the 2 right-hand diagrams on this curve. So there's the data somewhat favors the standard model, but it could be better. And there's another interesting case, which is the analog of this, where Higgs, very roughly, Higgs has a dilaton that couples to this operator instead of the standard model coupling. So here, the decay planes are parallel, but the polarizations of the Z are transverse. And this is excluded at something like the 1.5 sigma level now. So one really needs more data to settle that case. Nevertheless, as you see, the standard model expectation here is in very good agreement with distributions, a relatively small number of events that we have of this kind. I didn't talk about figure 1, but let's just talk about that for a minute. Figure 1 shows the distribution of the invariant mass for the 2 Z's and the 2 W's. What you see is that, of course, 1 Z and W must be very far off shell. These curves are done for a Higgs mass of 120 GeV, so please excuse me. But you see that the other one somewhat cheats to the direction of lowering the mass off shell in order to get the maximum cross-section. So really, in the accurate calculation, you have to treat both vector bosons as being off shell. Finally, the numerical values when you integrate over the phase space. The branching ratio for WW star, I think it's about 22%. And the branching ratio for the ZZ star, 2.7%. So when you multiply 2.7% by the square of this 4.6% to get leptonic decay rates, you get a very small number here, which you have to fight to study this process at the LHC. Because these numbers carry 2 off-shell propagators, they depend very strongly on the exact mass of the Higgs. And it turns out that both of these numbers satisfy something like delta branching ratio over branching ratio is related to the actual value of the Higgs mass, and then the coefficient here is 14, a very large number. So basically, to predict these numbers 1%, you have to know the Higgs mass to 100 MeV. And that's considered to be kind of the limit that the LHC will eventually get to with a very large amount of data. So this is something to watch for. To understand these modes very well quantitatively, you need to know the Higgs mass very accurately. Okay, now we are marching along toward the last important set of Higgs decays, which are the Higgs decays by radiative corrections. So, direct coupling to massive massless vector bosons, the two gluons and two photon final states. However, once again, if you have objects to which the Higgs is strongly coupled that can go off shell, you can get finite answers for these decay rates. So for example, for glue, you can draw this diagram, put top quarks in the loop, and take advantage of the large top quark Yukawa coupling at this vertex to get an answer of reasonable size. And for gamma gamma, you can do the same thing. Maybe I should say there are two diagrams. The other one is the symmetrical one. And then another thing that can produce the gamma gamma amplitude is a W loop. And here you have to be careful. All the things that come with W's when you do radiative corrections in a renormalizable gauge also have to be in that loop. So let me now try and estimate the size of these diagrams. So I'll start with this one here, the Higgs to a top quark loop to glue. Okay, now one way to do this analysis is just to compute the diagram. It's actually not very hard, and it's a very good exercise. And there's a surprise when you compute this diagram, which I'll let you folks discover. It's actually, there's a fun theoretical thing that happens when you compute this diagram. But I'm going to approach this in another way, using the insight that we talked about in the beginning of the lecture, that the Higgs couplings basically come from the shift of V to V plus H. So a nice starting point, first of all, we ought to figure out what the form is of the vertex that couples the Higgs to glue. So I claim that we can describe that by an effective operator. An appropriate effective operator has to be gauge invariant. And so the effective operator that couples the Higgs of lowest dimension, that couples the Higgs to glue is of this form, where F mu nu is the QCD field strength. That means that we're talking about a vertex, A mu B nu, which looks something like this. A times, K1 dot K2 epsilon G mu nu minus K1 nu K2 mu times delta AB. And you can now see that that vertex is gauge invariant. It's annihilated by when you dot it with either of the gluon polarization vectors. It's color singlet. It has all the right structure. This vertex means that A has the dimensions of 1 over mass. And now we can try and estimate what expression for K is going to come by calculating a diagram. So now let's say that A is generated by a diagram that looks like this. In principle, any quark flavor can circulate in this loop. But there's an interesting feature. The Yukawa coupling for a given flavor is MF over V. So we're always going to get an MF over V from calculating this diagram. Now, it has the dimensions of 1 over mass, so we need to get that 1 over mass from the loop integral. And so then we're going to get 1 over m, where m is the momentum, or the off-shellness that circulates in the loop. And now there are two very important cases. One where 2mf is less than mh. In that case, the Higgs mass flows through the loop. The momentum in the loop is of order the Higgs mass. And we're going to get 1 over v times mf over mh. Okay, so for the bottom quark, for example, this is a small number, and it provides a small correction to the next thing we're going to talk about. The other case is where the fermion mass is much larger than mh, And in that case, we get mf over v times 1 over mf, because it's the quark mass that dominates the off-shellness in the loop. Well, this is very cool, because now we get something of order 1, whereas before we got something that was highly suppressed in the quark mass. So it's a surprise. It's exactly the opposite of what you would expect. Those quarks that appear in Higgs decays make no contribution to the Higgs to glue-glue rate, whereas those quarks that are too heavy to appear in Higgs decays make an order 1 contribution. In the standard model, the only quark satisfying that criterion is the top quark, so that's why I drew the diagram in this way. In principle, if there were heavier quarks in nature, then those would also equally strongly, and as I say, independent of mass, contribute to this amplitude. In fact, this is probably the strongest piece of evidence that there are no quarks with the standard model coupling heavier than the top quark. Because let's say if there was another quark doublet, the Higgs to glue-glue coupling would be multiplied by a factor of 9. And that's really quite inconsistent with the picture of the Higgs boson that's emerging from the LHC data. Okay, well now we've got our toehold in this. Let's try and compute in a little more detail. So the next thing to study this amplitude, back and study the amplitude for 2 gluons and no Higgs bosons, namely the gluon polarization due to a top. And you folks have all computed that in your quantum field theory course, and it has the following structure. It's basically the diagram that gives the top quark contribution to the QCD beta function. So there's a trace of TATB. There is an alpha S over 3 pi, just like in the quantum electrodynamics case. And then there's a logarithm. It's a divergent diagram of lambda squared cut off at the lower limit at the top quark mass. Okay, now, the top quark mass is yt squared v squared. And if I vary that, what I get is the change in the d log 1 over m top squared d v is going to be 2 over v. So now we're in excellent shape. This derivative gives us Higgs coupling into this amplitude, the sum of these 2 diagrams, which are actually exactly the same diagrams that I drew before, just turned around in some way. The Higgs here is at 0 momentum. So what we're doing is making an estimate which is good when the Higgs mass is much less than the mass of the top quark, which is not, maybe I should say, such a bad approximation numerically. And so then we get as the value of these diagrams k squared g mu nu minus k mu k nu times delta AB times alpha s over 6 pi times 1 over v. That's a half. There's a 2, so 3 pi times 1 over v. And please notice that for 0 momentum Higgs bosons, this expression has exactly the same structure as this expression. So now we can just identify A is equal to alpha s over 3 pi v. And, or if you like, we can write that as g alpha s over 6 pi mw. And please notice that it's completely independent of the top quark mass, as I suggested by this order of magnitude argument. Okay, well now you put that in here, plug it into your phenomenological formula, and you get gamma of Higgs to glue glue is equal to alpha W alpha S squared divided by 72 pi squared mh cubed over mw squared. And numerically, this turns out to be a somewhat large number, something like, very close to a 10% branching ratio of the Higgs boson, given the small size of the other Higgs boson partial widths. By the way, as I said, it's not so incredibly difficult to calculate this diagram exactly. And when you do that, the leading order expression looks something like this. Higgs to glue glue is what I wrote before. Times the square of the following expression. The answer isn't simple, but it's not so hard to obtain. Okay, where tau is equal to 4m top squared divided by m Higgs squared. There are also, because gluons are coming out, the order alpha S QCD radiative corrections are important. When I quote a number, I'll take those into account. Okay, for the Higgs to 2 photon amplitude, we can go through more or less the same set of calculations and get an estimate of that also in the limit where the Higgs mass is much less than both 2m top and 2m W, because the W is going to come into that. So let me just correct what's going on here now for factor absent. What comes instead is a factor of 3 for color, and the quark charge, which is 2/3, appears here. We also need the vacuum polarization amplitude for the W's. And maybe I should just say those are the amplitudes that cause the W to renormalize the photon sampling. And we could try to, if you don't want to calculate it, you can just think of this as some amplitude in SU2 Yang-Mills theory and look at the contribution of the W to the beta function in SU2 Yang-Mills theory. And as you folks all know, I hope, that's the n of the gauge group times 11/3. And so the answer for this diagram is going to be k mu k nu times, this should be alpha over 4 pi, and then there's a minus 22/3, and then the logarithm of lambda squared divided by mw squared. The sign is different for the simple reason, as you guys know from Yang-Mills theory, the vector bosons contribute negatively to the beta function, and the quarks contribute positively to the beta function. So finally, if you add up all the contributions, you get k squared g mu nu over k mu k nu, alpha over 4 pi, this minus 22/3. Now, there's a little subtlety. When the W gets mass, a Higgs boson has to be involved, and that has to come into the beta function computation. So there's a plus 1/3. So this is from W. This is from the Higgs boson, which can be in the loop. And then there's a 4/3 times 3 times the quark charge, 2/3 squared from the top quark. Okay. Adding up all those things, what you find is that the Higgs partial width to gamma gamma has some structure like this: alpha W alpha squared over 144 pi squared. I hope I got this coefficient right. MH cubed over MW squared, just as in the previous case. and then this 21/4 minus 4/3. Okay. In any event, having done some work, one can then just put in the numbers, look up, because it's not such an easy calculation, the QCD enhancement of the Higgs to glue, and you get the following estimates for the branching ratios. Higgs to glue at 8.6%, and Higgs to gamma, because it's now alpha S instead of alpha and not particularly enhanced, 0.23%. And now we've pretty much gone through the whole family of Higgs decays. It's interesting that we computed a lot of numbers, but all of these numbers end at this very small one. Between the 1 and the 10% level, the BB bar at the 50% level. So given that we're going to accumulate a large sample of Higgs bosons at the LHC, by the end of the high luminosity LHC program, hundreds of millions of Higgs bosons, there's an opportunity to test all these standard model predictions and to test the size of a very large number of Higgs couplings. I was very impressed in the Higgs Discovery seminar at CERN on July 4th, 2012. Fabiola Gianotti noticed this point and said, "Thank you, nature." And indeed, it's a very nice property. The flip side of it is that it makes it very hard to discover the Higgs boson at the LHC because there is no dominant decay mode. But the experiments did actually overcome that problem. And so we'll talk about that in just a moment. So now, if you look at figure 3, this is a figure from the LHC Higgs cross-section working group, which gives the current predictions and their estimates of the uncertainty. Personally, I consider those estimates very conservative, but in any case, their estimates of the uncertainty and the predictions for the various Higgs decay modes as a function of the Higgs mass. So there's a huge amount of physics in this figure. And I think if you want to understand the Higgs boson well, you should try and understand the dependence of all of these curves on mass in an intuitive way. You see that over on the right, when the Higgs boson is relatively heavy, its decays are completely dominated by WW and ZZ. On the left, when it's very light, they're completely dominated by BB bar, and the various other fermions and radiative corrections come in a way which is quite interesting. So, as I say, to understand the physics that I've just tried to explain to you, you want to really study these curves in some detail and try and understand why they have the dependence on the Higgs that they do. On the other hand, now that we know where the resonance is, the curve is kind of irrelevant. You just draw a line at 125 GeV, and those are the predictions that you'd like to test at the LHC. Okay, so now let's talk a little about what the status is of the LHC analyses of these Higgs couplings, and what are some of the difficulties in trying to experimentally check the predictions that we've just worked out. So for that, the first thing we have to know is what are the main processes for the Higgs boson at the LHC. And there's one very simple thing to work out, which is that I just showed you that there's a partial width for the Higgs boson to decay to glue. So if we just time reverse that process, that means there's going to be an amplitude for glue to turn into the Higgs resonance. And this indeed turns out to be the dominant production mechanism at the LHC. Yes? Yes?
So this interaction with the dimension 5 operator.
Exactly.
But in order to make the in order to make the SU2 close to U1 invariant, we have the dimension 6 operators.
Yes.
And so I think the coefficient A is proportional to the V over some kind of scale m squared.
Yes, what you say is exactly right. So the SU2 cross U1 invariant operator, please excuse me for being a little sloppy, is something like,
so your naive calculation A is 1 over m, but
right.
I think that is the V over m squared.
Right. So maybe there's an A prime that looked like this. So A prime is of the dimensions of mass squared. But then if I put here the Higgs and a vacuum expectation value, that's A. And remember that A is of order 1 over V. So A prime is of order, A prime is of order 1 over V squared when you compute it with the Feynman diagrams. Naively, you would think that the A prime would have the top quark mass in the denominator, but it doesn't for the reason that I explained. It's compensated by a top quark mass in the numerator. So the more correct version of what I said is this argument here. Please excuse me. Okay, other questions while we're paused? Okay. Okay, so let's just go through this analysis again in a somewhat sketchy. Sorry, is this working now? Yes, okay. The Higgs to glue amplitude has some form I A mu nu, epsilon 1, epsilon 2, delta AB, mu nu. So I've compressed a lot of what I had in the previous argument into this A. Glue. Then I get I get 1 over 2 mh, 1 over 8 pi. They're identical gluons in the final state, so there's a factor of 1/2. The sum over colors gives a factor of 8. There's a sum over the gluon polarizations of A dot epsilon squared. And that very schematically is how you would do the width calculation. Equally well, we can do a cross-section calculation. That's 1 over 2s. S here is h squared. Then we need, please excuse me, spin averages for the two gluons. We need a color average for the two gluons, 1 over 8 times 8. There's still an 8 when I compute the square of the matrix element. There's a sum over the gluon polarizations of A epsilon times epsilon. And then there's one body phase space, which I showed you earlier in this course, is 2 pi times s hat minus mh squared. This should be an s hat as well. And what you can see is that these formulae have basically exactly the same structure, with the main unknown term appearing in the same place. And so there's a very general relation between a partial width and a production cross-section, which here we can write sigma glue to h is equal to pi squared over 8, gamma h to glue divided by mh times delta of s minus mh squared. And as you see, there are a lot of details about what the spin is of the various particles, what their color is, how you do the color average. You need to work that out for every particular case. But the general relation that a resonance cross-section is proportional to the partial width for the time-reversed process is a very general one. And you should always be looking for that whenever you encounter a situation like this. In any event, this turns out to be a rather large cross-section. When you fold this with the gluon distributions at the LHC, this turns out to be about 20 picobarns. Well, it's large by the standards of hard things that happen at the LHC. So this is the dominant cross-section for producing a Higgs boson. However, despite the fact that it's the dominant cross-section, it may not be the most useful one, because all this does is produce a Higgs boson somewhere in your detector and nothing else. Some of the Higgs decays are easy to see. Others are rather more difficult to see, as we'll discuss in a moment. And so you might want to produce the Higgs boson in association with some other signature so that you have a chance of tagging events as being very likely to be from Higgs rather than as being equally likely to be from other sources. And so there are three other processes that are important. First of all, the process that we analyzed yesterday in the lecture, WW fusion, and maybe I should also say ZZ fusion, because this vertex has, with longitudinal W's, strength of a Higgs sector coupling. This turns out to be a significant contributor to the Higgs production rate. It comes with two jets, which are very energetic, carrying most of the energy of the original partons. And because this cross-section is dominated by small transverse momentum of order MW, as I told you yesterday, those two jets go forward. And you can add the presence of those jets to the signature. So for this, you're looking at two forward jets plus a Higgs boson in the center of the detector. The second of these processes is the associated production with Z and W. And so these would be processes that look like this: a QQ bar annihilation into a W boson, let's say UD bar annihilation into a W boson, which then radiates a Higgs, and we end up with a process like this. The W boson, then you can look for leptonic modes, and you can separate the Higgs production from general QCD processes at the LHC. And similarly, with a somewhat smaller branching ratio, but with more fidelity, the Z decay. And finally, if you were able to make top quarks at the LHC, which, as I say, is a very large cross-section process, the top quarks can radiate a Higgs boson. And so this is another process, the associated production with TT bar. So, as we'll see, these two reactions are very important when you look for specific Higgs decays at the LHC, where the extra things that you produce in association provide some extra signatures that distinguish the events. And of course, the Higgs doesn't decay to the top quark. So if you want to study the Higgs top T-bar coupling, you need to look at this reaction at the LHC. So on the next figure, figure 4, what you see are the predicted cross-sections for these reactions as a function of center of mass energy. Please notice that this one has a very strong energy dependence, even when you go to from 8 to 13 or 14 TeV. Okay, so now we're ready to discuss how the Higgs can be found and studied in LHC experiments. And so the first thing that I'd like to talk about is just the consequence of glue to Higgs, and which produces a Higgs in the center of the detector and nothing else. But in principle, this competes with other even ordinary QCD reactions. And so in order for this process to be useful, what you need is some signature of the Higgs boson that's completely distinguishable from QCD and very readily accessible. Now, unfortunately, if you go down the list of Higgs decay, there are actually only 2 cases where that's totally unambiguous. And those are the cases where the Higgs decays to 2 photons, which, remember, is a 0.023% branching ratio in the standard model, and the case where the Higgs decays to ZZ star, which decays to 4 leptons. And the branching ratio for this whole process in the standard model is the amazingly small number, 4 times 10 to the minus 5. Nevertheless, these are very interesting decays because the objects have no quarks in them. They're purely either electromagnetic or electroweak final states. They're very distinguishable from QCD. Well, maybe I should say there is a process, QQ bar goes to gamma gamma, which is electromagnetic at the LHC. So this is a background on top of which this is a signal. The entire Higgs final is constructible, so you can form a candidate mass and look for a resonance on top of these distributions. And this number is something like 1 in 2 times 10 to the 12 pp collisions. So it's really quite an amazing feat to be able to identify these in terms of just the raw number of proton-proton collisions that you have to search for. Nevertheless, these are the modes in which the Higgs was eventually discovered. I put in the notes the current status of those, basically in one case each for the experiments. So what you see in figure 5 is the CMS spectrum of the gamma-gamma mass after appropriate selections to remove most of the signal where the gammas come from pi zeros. And what you see is that there's a smooth background which comes from this QCD electromagnetic process. And then on top of that, there is a small but very significant bump. And background subtracted, it maybe looks a little more significant. And so that would be the signature of the gamma-gamma resonance, which is this new particle at 125 GeV. In figure 6, what you see is the mass spectrum of 4 leptons collecting these 4 lepton events. This is from Atlas. In each case, there's a comparable plot from the other experiment. There's a very significant signal over a small background, but if you look at the numbers, it's very scary. There's about 15 events in that peak corresponding to this small number. So it's a very noticeable signal, but people have to work very hard. Actually, there are only about 25 events theoretically produced in the entire LHC run of this Higgs to 4 lepton type. So the efficiency for gathering these events is really very large. And let's just say this is one of the things for which you need a several thousand member collaboration to find all the tricks to pick up the maximum number possible of these events in order to make a discovery such as the discovery of the Higgs boson. Okay. In figure 7, I show you an event display of an event which is a candidate for PP to Higgs to ZZ star to E plus E minus mu plus mu minus. And you see it's a very beautiful event. The electrons are seen calorimetrically in the Atlas detector. The muons penetrate to the outer tracker. The total mass that's measured in that case, I think, is very close to 124 GeV. So ordinarily, when you see an event display at the LHC, it's only a candidate, but this one is actually very likely to be a Higgs boson. Okay. The next thing that I'd like to discuss now, okay, this particle really exists. The evidence for it statistically is extremely strong. The next thing that we have to do is to talk about the observation of the various decay modes that I've discussed in this lecture. So the next one we should discuss, which is the other one which is done in the generic mode, glue to Higgs, is the Higgs to WW. Now, this is already much more challenging. So the process we're interested in is glue to Higgs to WW star. And then in order to get this out from under QCD, we need to look at leptonic decays on both sides. So it's L plus nu, L minus nu bar. The neutrinos, as I've emphasized, are invisible in the LHC detectors. So basically, this is just L plus, L minus, and missing energy. And once I say that, you can see it's really kind of scary, because there are lots of very reasonable processes. For example, QQ bar to W plus W minus to the same final state that are also going to give L plus L minus plus missing energy. And it's just not so easy to distinguish this signature from this almost identical signature. There's some properties of spin and angular distributions that you can use to help you a little, but ultimately what you have to do is to very carefully estimate the cross-section for this process and see if there's an excess that could be attributable to the Higgs boson. So some sense of that is given in figure 8. So what you see in this figure is the ATLAS data for a selection of events for this reaction. Some attempt has already been made to use the angular distribution of the Higgs decays to eliminate some background. But as you see, most of the events that are seen are actually accounted for by WW production. But nevertheless, there is a small but significant excess that can be attributed to this process. And so this process actually does seem to exist and has a strength which is roughly in accord with the standard model expectation. Now, when we go on from here, we come into processes which are just very difficult to see with the Higgs boson alone on top of the standard model backgrounds. And so for the next analysis that I'd like to discuss, that's the analysis of Higgs to tau plus tau minus. The best evidence so far comes from the vector boson fusion process, where we're looking for PP going to 2 jets in the forward direction, plus a tau plus tau minus decay. The analysis is quite complicated because, as I've told you already, the tau has numerous decay modes. So the strongest evidence probably comes from modes where one tau decays leptonically, the other tau hadronically, which generally means to one charged pion plus other electromagnetic deposition. And then you use these 2 jets in the forward direction to tag this as an unusual process, which is not typically seen in QCD. So there's an event display in figure 9, which gives a feeling for this. It's actually a very beautiful event. 2 very forward jets. Please notice that one of these jets almost necessarily has to be outside of the tracking volume. The part of the signature is that the delta eta of these jets is greater than 4 in order to insist that they're sufficiently forward that they're in this process rather than in other modes of Higgs QCD production. In the case of this figure, one of the taus is decaying to an electron and 2 neutrinos, the other one to a muon and 2 neutrinos, and you see the electron and the muon signal in green and red on this event display. Maybe I should emphasize here, this is only a candidate, and we'll talk about the probability that it's a Higgs boson in a moment. Okay, now, there's an obvious problem, because whenever you have a tau, you have neutrinos. So here there are 2 neutrinos, here there's a neutrino, and there are probably also pi zeros in this decay. And so it really becomes a problem, how do you work backwards from what you see to find a tau plus tau minus signal and associate it with a resonance at the mass of the Higgs boson? And so here there's a trick which was introduced, and we'll see that these tricks, I'll discuss a lot of these tricks in the next lecture, but there's a certain bag of tricks that you need in order to do collider physics, and this is a very nice illustration of one of them. So when I see this process, for example, what I'll see is, let's say, a muon which goes in this direction, a pi plus, which goes in this direction. There's also some missing energy associated with both of these particles. And what I'd like to do is to figure out what is the mass of the progenitor so I can try and associate that or not with the mass of the Higgs boson. So there's a nice way to do this. The tau is a very light object. Its mass is basically 1.8 GeV. And so if it's highly boosted, it's going to decay very much in the forward direction. That means it's a very good approximation that the missing neutrinos are more or less parallel to the mu minus here, and over here that the missing neutrino and maybe pi zeros are almost parallel to the pi plus. So let's assign the p minus to have this direction, but we don't know what its magnitude is. Let me write that as E minus times n mu. And over here, we have a momentum vector, which again is E plus times n plus mu, where we know the direction, but we don't know the magnitude. Now, these vectors are actually in 2 dimensions, and they recoil against a transverse momentum, which is order mw, which comes from the forward jets. So now let's take this system and work out the missing ET, which is a 2-dimensional vector in the transverse plane. So in this process, there's supposed to be exact momentum balance between the 2 jets and the Higgs. So we know exactly what the momentum is, 2 dimensions of the tau plus tau minus system. So that's 2 constraints. We have 2 unknowns. So you can solve the problem and determine the parameters E minus and E plus. Once you've got that, you've got the 4 vectors of the 2 taus, and now you can add them together and get an estimate of the tau plus tau minus mass. So the information is there, but it's just a little tricky to get it out in the Hadron Collider environment. The mass solution is not so bad. The delta M H for a Higgs boson is something like 15 GeV, so that at least is enough to separate the Higgs boson from the Z0, which is going to be a very important background. Okay, well now we have to ask, what does this really look like when you begin to collect events? And the problem is that there are other particles that can be produced even in the vector fusion and in other mechanisms that you have to think about. One very important one, probably the most important one, is that a Z boson can be produced in W fusion. And the Z then has this 2.3% branching ratio to tau plus tau minus. And if you put everything together, this is a larger cross-section than the Higgs cross-section, so you'd better understand it extremely well. Fortunately, there's a way to understand it well, because the Z also decays to E plus E minus and mu plus mu minus. So you can collect events which are E plus E minus and mu plus mu minus plus 2 jets, understand them thoroughly, and then basically in simulation substitute the tau plus tau minus signals for the E plus E minus or mu plus mu minus signals. And so there's some slides from the CMS analysis in figure 10, and you can see what the selected distribution of events looks like. And that tan, the big tan peak, is this process, which fortunately you can estimate the size of that process in this analysis quite accurately by the method that I've just described. There's another important background, which is PP to W plus W minus, where one of these will decay leptonically and the other hadronically to 2 jets. And if you have another jet from the initial state somehow, it's relatively easy to create the signature that we're talking about here. These 3 processes, the Z, the W pair, and the Higgs production, all have different dependencies on the reconstructed resonance mass. And so trying to use that dependence, you can separate these. However, if you look at these curves, you see that it's scary. The little dotted white region in figure 10 is the prediction for the Higgs rate. It's completely overwhelmed by the standard model background. But once again, with a large enough event sample and accurate measurements, you can convince yourself that there's an excess of signal over background and try and then use that to estimate the rate of the Higgs production process. Now, finally, let's talk about the dominant decay mode, which is Higgs to BB bar. So first of all, we can talk about glue to Higgs to BB bar. So the signature for that would be you look at an LHC event, you find two jets, you insist that each of those jets is B-tagged, that is, it has a displaced vertex characteristic of a B-quark decay, displaced by, let's say, several millimeters from the interaction point, and you use that as a signature. Unfortunately, as we saw in the, I guess, the fourth lecture, there's a QCD cross-section for glue to BB bar, and this cross-section is 1 millibard. Even if you say that the mass of the BB bar is of order 100 GeV, the cross-section is something like 10 microbarns. And remember that the cross-section here is 20 picobarns times the 60% branching ratio of the Higgs to BB bar. So in terms of this strategy, you're missing the signal over background is something like 1 in a million. And it's just very, very difficult to try and find a signal in that circumstance. The strategy that used by the experiments is to look at a situation with a vector boson. So for example, if we look at Higgs to Z, over here, Z to L plus L minus event as being somehow special, independent of QCD, and we get out of the standard backgrounds. However, all is not simple. There is a process QQ bar annihilation to ZZ. So here we can have plus L minus, and here Z to BB bar. And this is more or less the same signature as the process that we're looking for, and the cross-section when you evaluate it is numerically larger. Also, you can have QQ bar to Z to L plus L minus plus a gluon, and gluon splitting to BB bar. And this, remember, is an order 1 QCD process. So these three reactions, this, remember, is a 15% branching ratio. These three reactions are all very important, and they all have sections that are of the same order of magnitude. So now what you have to do is really study in great detail what are the subtle differences between these three reactions and try and prove that there is some of this on top of these. The dependence on the BB bar mass is slightly different for these reactions. That gives you one handle. And you can actually take advantage of the fact that this BB bar system is colored, whereas over here it's color singlet, to get a little more advantage in the selection. At the moment, what shall I say? CMS claims to have evidence for this process, quote, evidence that is more than 3 sigma. Atlas claims not to have evidence. It's kind of a look of the draw, and this is something that we hope will be clarified with much larger event samples and probably also more incisive analyses in the coming run of the LHC. Okay, well, this is now what is known experimentally about the Higgs boson from measurements at the LHC, and there's a summary of all these measurements that you'll find in figure 11. So I'd just like to say a few words about what is actually plotted in figure 11 and some orientation to that. So what the LHC experiments quote in terms of a test of the standard model hypothesis for the Higgs boson is something called the signal strength, mu. And mu is equal to, for a Higgs decay to AA bar, for example, the cross-section for pp to Higgs by the reaction that you're using in the experiment to AA bar divided by the standard model expectation. So this is the signal strength. It's something you can measure. You try and measure the cross-section in the numerator. You ask your theorist friends to calculate the denominator. You take the ratio, and those are the numbers that appear in this table in figure 11. The signal strength is a little subtle, and it's important to realize that. So let's, for example, think about the signal strength for pp glue, that is, to a Higgs boson to gamma gamma. So the signal strength for this reaction is proportional to the cross-section for glue to Higgs, which I told you is proportional to the partial width for Higgs to glue. Then the branching ratio for Higgs to gamma gamma, which is the same thing as the partial width for Higgs to gamma gamma divided by the total width of the Higgs boson, which, remember, I told you is a very small number that can't be measured directly. This is, in the standard model, dominated by BB bar, but remember, the BB bar is understood rather poorly from the experiments. So let's say that, well, you look at this table and you look at the ATLAS result, and the central value is 1.55. So you say there is an enhancement in this particular quantity if you believe ATLAS and ignore CMS. And maybe that's, as a theorist, I'm interested in that. Okay, well, now you see that enhancement might be an enhancement in the Higgs to gamma gamma partial width. It might be an enhancement in the Higgs to glue partial width. And it might be suppression of the Higgs to BB bar partial width that dominates the denominator. And so you have to look at the whole picture to figure out which of these different hypotheses is the most likely. And actually, it's not so easy, especially because there's so much uncertainty about what the denominator is in this expression. So that's the current situation, but certainly we hope that with many, many more Higgs bosons being observed at the LHC in the next actually 20 years, and maybe even new experiments in other environments, we'll understand this a lot better. One of the things that I'm very excited about is the possibility, maybe 15 years from now, of having an electron-positron collider. There's a proposal called the International Linear Collider that's being now considered in Japan to do E+ E- collisions that produce the Higgs boson and maybe measure things to a much higher degree of accuracy. So there's a very coherent standard model theory of the Higgs boson. I've tried to emphasize in this lecture that it's subtle. There's a lot of physics, and it's worth your serious study. We have no idea whether this picture of the Higgs boson is actually the correct one. There is a lot of opportunity for the Higgs boson to be influenced by new physics beyond the standard model that we haven't yet discovered. Maybe we'll discover it for the first time in seeing the deviation of the Higgs boson properties from the predictions that I've described in this lecture. And as I say, this is going to be one of the major roads of investigation for new physics at colliders. So please study hard and tell us where we can find the new physics. Thank you very much. Okay, more questions? Yes?
I have two questions.
Please.
So one is how is the difference between the calculation and the calculation in the signal?
I'm sorry, I didn't. Could you repeat that?
How is between the fluid calculation and that approximation in the signalist length?
Oh, there's no approximation here, or rather, the approximation here is the narrow width approximation, that the Higgs is a very sharp resonance compared to other background processes. And the Higgs is so narrow, as I say, 4 MeV on a scale of hundreds of GeV. This is a very good approximation. So the fact that mu is proportional to this quantity is, I think, an extremely good approximation. If something fails here, that's not what's going to fail. Second question?
And the other is that I know that in the ILC, we can observe the Higgs triple couplings.
Yeah, yes.
But is it possible in the LHC?
Oh, this is an interesting question. And actually, even this week with Professor Contino and others, we've been talking about it. Observing the triple Higgs coupling is very difficult. It's considered in any experimental environment. And let me give you a little feeling for what that takes. So let me draw some diagrams that contribute to the triple Higgs coupling. At the LHC, the most attractive way to do it is to look at glue producing a Higgs boson, which then couples to 2 Higgs bosons. So you're looking at double Higgs production. People have also considered looking for double Higgs production in vector boson fusion. So this would be the reaction, where, for example, you have WW to a Higgs boson, which couples to 2 Higgs bosons. And in the ILC, so this is an E plus E minus environment, you could imagine doing this in E plus E minus to Z going to 2 Higgses, or in W boson fusion again. The same diagram that I drew over here. Interestingly, for 2 Higgses, it's also dominated by double longitudinal W boson production. Now, the problem is that these processes don't stand by themselves. So when you have this process, for example, there's also a box diagram that looks like this. And the cross. And you have to add these 3 diagrams coherently. And it turns out they have destructive interference. So this is actually, when you have a larger coupling here, you have a smaller 2 Higgs production rate. And that's true for all of these processes. For example, again here, in W fusion, both in this case and that case, this diagram is actually larger, and it interferes destructively with this diagram. And there's a similar thing that happens over here. So this is the first thing that you have to worry about. The second thing that you have to worry about are that the cross-sections which are predicted are really small. So for this process here, you're talking about tens of attobarns, not femtobarns. And here you're talking about attobarn type cross-sections. Sorry, no, it is, Roberto, it is femtobarns. Tens of femtobarns and femtobarn cross-sections here. But, you know, it means that you get, you know, 10,000 or 1,000 of these processes, and you have to pick them up. But now, how do you pick them up? Well, especially in the hadronic environment, the Higgs boson is not a very characteristic object. The dominant, we haven't even talked about the branching ratios. The dominant decay is BB bar, and there are, as I've already emphasized, a very large number of ways of producing BB bar. And so the strategy I think that's thought at the moment to be the most attractive is to look for a Higgs to gamma-gamma decay, which, remember, cuts down your signal by a factor of 1 over 1,000 or 1 over 500. But maybe you get a factor of 2, 1 over 250. And then over here, you look for a BB bar decay. So all of these things make the measurement very difficult. And actually, in both environments, the measurement is quite difficult. So you have to actually find the Higgs. So you need some very characteristic channels in which to find the Higgs. You have to reconstruct it. You have to realize that the thing you want to measure is part of a sum of cross-sections, and there's destructive interference. It's very scary in any of these environments. I think at the moment, the measurement is best understood in simulation in the ILC. And people claim that with the full ILC program, so this is 20 years of running the ILC, you maybe can measure it to something like 14%. And in the full LHC program, the number here is debated, and people talk about numbers like, well, maybe observing it at 3 sigma. So either way, it's just very difficult. On the other hand, maybe I should say that there are theories of physics in the standard model where this coupling can be larger by a factor of 2. So maybe just observing it or observing it at the 10 or 20% level is enough to break through into physics beyond the standard model. Okay. Anyone have a less sophisticated question? Please.
You explained. Just speak up. You explained that it's very hard. You explained that it's very hard to pin down the decay of the Higgs. So I guess it's even more difficult to pin down the invisible part. Still, like something that's still. Can you maybe say something about current status?
Oh, well, the invisible part of the Higgs with, I think there's really no choice but to measure it directly. And so what you need is some process where you tag a Higgs decay with some other object, and then there's something missing. So at the LHC, for example, in the process of Higgs production with a Z boson, you could have H goes to invisible over here. You could have the Z to L plus L minus with a transverse momentum of order m Higgs, so that's rather characteristic. You look for events of this type, and you write that as a bound on the Higgs goes to invisible width. Now, unfortunately, again, it's tricky because there's an important background, namely that the Z goes to neutrinos 20% of the time. And so this signature looks exactly like this signature. And so once again, you have to carefully normalize this reaction and see if there's some excess with respect to that. So I think someone should correct me if I'm wrong. I don't have the number off the tip of my tongue, but I think the Higgs to invisible branching ratio is known to be a less than about 40% branching ratio at the moment. Now, in E plus E minus, you can do a lot better because in proton collisions, you don't know the kinematics of the initial state. But in E plus E minus, you have a very good idea of the exact kinematics of the colliding electron and positron. And so you can consider this reaction. And now H is going to go to invisible. And at a center of mass energy of 250 GeV, with the known Higgs mass, this Z boson has an energy which is more or less exactly 110 GeV. Even in the hadronic modes of the Z decay, you can look for a Z, this energy in the lab, and whatever's on the other side is the Higgs boson. And so then you can get to below 1% in the kind of limits that you would be able to quote on the invisible width of the Higgs. So once again, the strategy is you have to measure this directly and add that to the information. And basically the way you're going to get the total width of the Higgs is you measure all the decay channels. Every one in this setting can be visible, and you add them all up, and whatever you get is the total width of the Higgs. So you can actually make a model-independent analysis that gives you as an output the total width of the Higgs, but you can't make that measurement directly. Other questions? Please. Yes? No, it's the standard model expectation for the Higgs process that you're measuring. So the signal strength would be 1 if the standard model were exactly correct. Just that's the definition. Okay. Okay, other questions? Okay, we're coming now to the end of the time when I'm in Firenze, but at least I'm here today and Monday morning, so please get your questions organized, or over the weekend send me email and we can talk some more about all these things. Thank you very much. Oh, sorry. Yes. Yes. So the question is, I didn't tell you about the radiative corrections to the calculation of Higgs to glue to Higgs. That the QCD perturbation series for PP, that is glue to Higgs, is rather awkward. There's a 0th order result. There's an alpha S squared, and actually the alpha S cubed, or some good approximation to that has recently been computed by people in Zurich. The orders of magnitude are 1 plus 20%, plus I'm not sure quite what the answer is here, but it's a very slowly convergent perturbation series. And so this is certainly something that contributes to the uncertainty when you try and estimate the signal strength. The reason for this, I don't think I can give you a good explanation for, except just the fact that the gluon couplings to gluons are large. So typically you get large radiative corrections whenever you have a gluon-gluon reaction. The first radiative corrections to this look like that. The second radiative corrections again involve gluon splitting. And these are just numerically large terms, and there's not much you can do about it. I wish I understood this better, but I don't. Excuse me. Okay, anyone else? Good. See you on Monday then.